Okay, so this is our intro to the lab number 4. So we're still having the inclined ramp, but in this case we're going to hang a mass vertically and we're going to either slide a block up the incline or we're going to have a cart go either up or down the ramp. And that'll depend upon what the hanging mass is. So a certain amount of mass will pull, say, let's talk about the cart. If the mass is high enough, then the cart will be pulled up the ramp. If this mass is small enough, it'll roll down the ramp. Now, the way we measure velocity in this particular lab is at the top here, we have a wheel, which I have expanded. And over the wheel, we put the thread, which connects the two masses. So when this thing moves up at a certain linear velocity, this thing will rotate at a certain angular velocity. And because the thread, as long as the thread is not sliding relative to what's called the pulley, then the linear speed of the thread, which will be the linear speed of the masses, will be the linear speed of the surface of this wheel. So the way the measurement is done is we have a photogate which shines a light between the spokes. And when the spoke blocks the light, then we get a reading, just like we did with the photogates when they went through linearly. And if we know the radius of the wheel, we know the circumference of the wheel, which is the distance around the wheel, which is 2 pi times the radius. Now, if you have 6 spokes on this wheel, each time the light is broken, we will have traveled 1/6 of the circumference. So if you take 2 pi r and divide by 6, you get pi times r over 3. So that gives us a distance. So we'll have times and distances. From that, we can calculate velocities. And just like we did with other previous labs, we take the slope of the velocity versus time curve, and that gives us the acceleration. So we can measure the acceleration of these objects, either up or down the ramp. So that's the basic idea. So we're going to look at three different situations. So here's the lab explanation, and you can read it. I'll post it, but we're going to measure the ramp angle, just like we did before with the angle indicator, not using the rulers. We're going to measure the mass of the cart, which is the same cart that we've been using, and we're going to measure the mass of a block, which has no wheels. So scenario 1, which is 2 scenarios, but we're going to do 2 conditions with scenario 1. First thing is we're going to see what is the minimum mass to keep the cart stationary. So let's go back here. So if this mass multiplied by the sine of the angle is equal to this mass, or the weight, the x component of the weight here is equal to the y component of the weight there, then they'll be balanced and nothing will happen. But there's a little bit of friction in the wheels and in the pulley. So there's probably a maximum weight we can put on here when it just starts to roll up the incline. And then if we remove weight from here, there'll be a minimum weight we can have here, which will, before this thing rolls down. Now, I don't know what this is. I haven't run this experiment before. But what we'll do is we'll measure those 2. We'll estimate the mass needed by taking the mass of the cart, which we've measured up here, and multiplying by the sine of the angle, the ramp angle. One thing we have to do here is remember to add 5 grams to the masses that we put on the hanger, because the mass of the hanger is 5 grams. So if we put 100 grams on the hanger, we're really adding 105 grams on this vertical mass. These may be exactly the same number. I think there's going to be, there'll probably be a slight difference, maybe a gram or 2. Then what we'll do is we'll find out what the maximum mass we can stick on hanger just before it starts to slide up. And then we're going to add increments of that amount. So we're going to add 20 kilograms more than this value here, 40 kilograms, 40 grams, 60 grams, 80 grams, and 100 grams. With those additional masses, we'll measure velocity versus time. We'll look at the slope of that. We'll do that experiment 5 times, which we should be able to just do, we won't have to stop the readings. We'll get 5 slopes that we can measure the slope of. We'll enter those in. We'll put the total amount of mass that we have. So let's say this is 120 grams. We'll put in 140, 160, 180, 200, 220. So we'll just add these amounts and we'll record those total amounts of mass here for the 5 conditions. We'll measure the acceleration and then we'll average them. Okay, so that's the first part. Next, we'll go the other direction. We'll remove 20 grams from the minimum mass. So then, when we have not enough mass here, then it'll accelerate down the ramp instead of up the ramp. And we'll do the same increments, and we'll fill in the table as such. So these are going up the ramp, these are going down the ramp. So those are the frictionless conditions. The next one is similar, except what we're going to do is we're going to replace the cart with a wooden block. And we're only going to go in one direction, which is up the ramp, because it may not slide down the ramp even if you take all the mass off. So what we'll do is we'll keep adding mass here until this thing just starts to slide. We'll record that amount just before it starts to slide. And then we will add 20, 40, 60, 80, and 100 grams. So then it'll, as we add more mass, the cart will accelerate more quickly. We'll take 5 readings for each condition. We'll average those accelerations to get an average acceleration. Now in the middle, when we do the 60-gram condition, we'll also download the raw data to a USB drive so that we can analyze one of the runs that will have basically what you'll see, the kind of situation you will see is velocity versus time, and you'll have like this, and it'll go like that, and we'll measure the velocities here and find the slope. So the one, this is for each one of the 5 runs, and we'll download all that data for one run to a text file to look at later. Now one thing here, interestingly enough, is if I plot x versus t, the points will be plotted such that the change in x will be constant because it's going to take a measurement every certain distance along this wheel. The time values will get closer and closer and closer together. So this, in this case, the increment in the x direction is constant, and the time gets closer and closer as the thing accelerates. And you'll see the same kind of thing if you plot velocity versus time. But we will get a linear region as the objects accelerate, and the slope of that line will be the acceleration. So as the object accelerates, the points get closer together on the time axis, but they're equally spaced on the x-axis. Now this is a kind of calculation that we'll do. This was just me figuring out what kind of accelerations I should expect. We'll find out for the frictionless cart scenario that the equation for the acceleration up the ramp or down the ramp is equal to the hanging mass, and you can either use grams or kilograms because we have mass in both the numerator and the denominator. So this is the weight of the hanging mass, and then this is the x component of the weight on the ramp. So we have m1, that's going to be the mass of the cart or the block, times g times the sine of the angle theta. And then we divide by the total inertia, m1 plus m2, and that will give us some idea. So what I did was I just did some guesstimates, and it looked like when you add 20 grams, the first step, you get about 0.33 meters per second squared acceleration. And if you add 100 total grams, which is the end, the fifth condition, you should get an acceleration of around 1.40 meters per second squared. And you know, some of the ones that we've done when we just let it run down the ramp by itself have been on the order of 2 point something meters per second squared. So I wanted to pick, you know, what kind of, that was giving me an idea whether the amounts of mass that I add here, incremental, would be appropriate. Okay, so that's it.